So in Chapter 3, Section 1, we're going to be talking about functions and some of their properties. So the first thing we want to talk about is whether or not a relation represents a function. So let's define what a function is. A function is a rule that pairs each input, and for this that's usually x, with exactly one output, which is usually y. So a function is just a rule that pairs inputs and outputs. The extra thing that we need to make it a function is that each input pairs with exactly one output. So let's do example number 1 to help illustrate what this means, and more importantly, what it doesn't mean. So we want to determine whether or not the following correspondence or relation represents a function. So our domain is going to be the set of students in this class. Our correspondence or our rule is each student's current grade, and then our range would be the possible grades that you could have in this class, which is an A, a B, a C, a D, or an F. So to determine if this is a function, we need to determine, does each input go to exactly one output? So the question is, so our inputs are students and our outputs are grades. Can a student have two different grades in this class? So in other words, can you have both an A and a C in this class at the same time? No, you have exactly one grade. You can have an A or you can have a C, but you cannot have both an A or a C. So this would represent a function. This definition often gets confused with the idea, which is the following. So now, is it possible for every student in a class to get an A? Sure, right? Every student can have an A in a class. So our definition doesn't say anything about different inputs having the same output. In fact, it is entirely possible for different inputs to have the same output, or that every input has the same output. That's okay. So this definition says that each input gets paired with exactly one thing. So one student, one grade. All students can have the same grade. That's fine. So be careful where we're putting the exactly one. So we don't say that all of the outputs have to be unique. We just say that each input goes to exactly one output. We'll talk about some other definitions involving functions a little bit later today. All right, so now here's a quick try for you guys. Determine the domain and the range of this relation and tell whether the relation represents a function. Now remember, our definition says that each input goes to exactly one output. All right, so let's find our inputs first. So our inputs are our first coordinate, so usually x, and we would have 4, 7, 100, and negative 81. And our inputs are also going to be our domain. And then we have our corresponding outputs. We have 6, 6, 6, and 6. So our output is just going to be 6, and that's going to be our range. So for this rule, we're told that every number that's in the domain, so all of our inputs, 4, 7, 100, and negative 81, all go to 6, which is they all have the same output. So is this rule a function? And the answer is yes, right? This is the same as every student can have an A, right? So all students can have the same grade, but each student can have only one grade. So an input, say 4, couldn't have another output listed, so I couldn't add the ordered pair 4 and 10, because then the input 4 would have the output 6 and the output 10, and that wouldn't make sense. So that would be an example of a non-function. All right. So the next thing we want to talk about is evaluating our function at a couple of points. So this formula that we're going to talk about will make a comeback later on, or at least part of it will. So our goal is to evaluate given that g of x is equal to x squared minus 4x plus 4, find each of the following. So when we have function notation, remember g of 2, what's in our parentheses? That is our input. So when we say g of 2, we are going to be replacing all of our x's with the value of 2. So that is going to be 2 squared minus 4 times 2 plus 4. And we simplify, getting 4 minus 8 plus 4. So in that case, we get 0. So that's going to be our output. So we write g of 2 equals 0. That is an input-output pair, right? So that's our input. And this is the corresponding output. We want to note that this is just a different way to write an ordered pair. So this is the same as 2, 0, right? The input g of 2 equals 0 is the same as the ordered pair 2, 0, because my x is my input and the 0 is the corresponding output. It's just two different ways to write the same thing. So they're both ordered pairs. One in function notation, one in the classical ordered pair notation. All right, our next part is we want to find g of a. So that one says, everywhere I see an x, I'm going to replace it with a. So I have g of a is going to equal, just like what happened above. Instead of replacing it with 2, we're going to replace it with a. So I have a squared minus 4 times a plus 4. And that's going to simplify to a squared minus 4a plus 4. So the net effect of that was, if I replace x with a, I get the same numbers back. The only difference is now my variable is a instead of x. So in that sense, the variable behaves like a dummy variable, right? Now if I made a equal to 2, I would get exactly what I had in the previous line, right? So it's acting as a placeholder for an unknown number. All right, let's calculate our next one, which is g of x plus h. So if I replace all of my x's with x plus h, I'm now going to get the binomial x plus h squared minus 4 times x plus h plus 4. So now to simplify this, I need to do a little bit of work. So this one I need to distribute out or FOIL, and if I multiply a binomial by itself, I'm going to end up with x squared times 2xh plus h squared. And let's do that over here on the side if you don't remember that that's the product. When we multiply something, when we square something, we're multiplying it by itself. So we would have to FOIL this thing out. And if we did so, we would get the following. X times x and x times h would give us x squared plus xh. We're then going to get h times x and, or h times x and h times h, so that's going to give us another xh and an h squared. And if we collect our like terms that we have right here, x plus h, or x times x plus x times h gives us 2xh. We have our x squared and our h squared. We then distribute our negative 4 into our parentheses here, and we would get negative 4x minus 4h plus 4. So finally, after all of that, we get g of x plus h is equal to x squared plus 2xh plus h squared minus 4x minus 4h plus 4. All right, now our very last part is we wish to calculate the following formula. G of x plus h minus g of x all divided by h. So essentially what we're going to be doing is evaluating this formula at the given values. So we just calculated g of x plus h. Well, that's this part of our formula. We are also going to need g of x. Well, g of x was our original function that was given, and that's going to go in here, and then h is just part of our formula. So this is going to equal to x squared minus 2xh plus h squared minus 4x minus 4h plus 4, take away g of x, and our g of x was x squared minus 4x plus 4, and then that whole entire thing divided by h. All right, so now we just start simplifying. So we have x squared minus 2xh plus h squared minus 4x minus 4h plus 4, and we distribute our minus sign in, and we get minus x squared plus 4x take away 4, once again all divided by h. So a couple of things are going to reduce out. I have a positive x squared and a negative x squared. I have a negative 4x and a positive 4x. And I have a positive 4 and I have a negative 4. So they reduce out. And that leaves the following. Negative 2xh plus h squared minus 4h and then everything else reduced out over h. We now have a common factor of h, which we can factor out. We get negative 2x plus h minus 4, all divided by h. And now our h's reduce out, leaving, after that entire computation, negative 2x plus h take away 4. And that would be what we would get at the end of simplifying. All right, so it appears I made a typo in my transcription here. That should be positive, which means this one should have been positive. So that's positive, and that's positive. So we get 2x plus h minus 4. So one thing we do want to take note of when we are resolving this type of formula, when you resolve a formula that looks like this, or one that has a plus h minus g of a, the h's will always reduce out. If they don't, something went wrong with the algebra. This is a special formula that you will use extensively next semester in calculus called the difference quotient. So it has a lot of applications, so just keep that in mind, but one of its properties is that the h will always reduce out if it's been simplified correctly. So keep that in your mind as a check step as you move forward. All right, so functions can be represented in many different ways. So the next way that we can talk about a function is to represent it graphically. So graphically is just a way to visualize a whole bunch of ordered pairs. So if we take a look at example 3, we have the graph of the function f of x is shown. Find the function values negative 3, f of negative 3, f of negative 7, and f of negative 2. So if I want to find f of negative 3, that's my input, or my x. So my inputs will always be on the horizontal axis, and my outputs will always be on the vertical axis. So to find the output for negative 3, I go to my input negative 3, and then I go up or down until I touch the curve. And that will give me that point on the graph. So at negative 3, the output, or the vertical axis, or the y value is 5. So that would give me that f of negative 3 is equal to 5. I can do the same thing for negative 7. I go to negative 7, and I'm going to go down until I touch the curve. And then I go to the right here, so I'm going to get the ordered pair negative 7, negative 3. So f of negative 7 is negative 3. For our last one, we would go to negative 2, and we go up to 2, so then we would have f of negative 2 is 2. All right, so let's go ahead and read off our values. So if we go to 3, and we go down to our graph, we look like we're going to get negative 9. So g of negative 3 is 9. If we go to 6, we're actually right on the horizontal axis, so g of 6 is going to be 0. And g of negative 1, looks like we're going to go all the way up here. We're going to get g of negative 1 is 7. And those would be our outputs from our graph. All right, so another way that we can represent functions, instead of as a rule or as a graph, we can also represent them as a table. So use the table below to answer the following questions. Evaluate f of 3 and solve f of x equals -4. So to evaluate -3, we need to find our input of -3. And if I input -3, the corresponding output is -6. So f of -3 is equal to -6. Our next one, we're asked to find the x value where our output is 4. So we're going to be using our table backwards. So we find our output of -4, but we notice that it comes in two different places. I have an output of -4 here and an output of -4 here. So this equation is going to have two solutions. So we're going to have x equals the corresponding input of 1 and 4. So x is equal to 1 or x is equal to 4. And both of those have the corresponding output that we wanted. That is f of 1 equals -4 or f of 4 is also equal to -4. So we can solve for inputs and outputs using a table by recognizing each of them as the corresponding input or output of what we are looking for. All right, the next thing we need to talk about is a definition called the vertical line test. The vertical line test is a graphical way to test if a relationship is a function. So, the vertical line test says the following. If there exists a vertical line that intersects a graph more than once, then the graph does not represent a function. So this statement says, if there exists any vertical line that intersects the graph more than once, then the graph does not represent a function. So let's look at a couple of examples. So determine if the graph represents a function. So I'm going to start in the middle because I want to ask a question. So if I draw a vertical line here at x equals 6, it touches that graph exactly once. So is that graph a function? So the answer is no, right? Because it doesn't say if you can draw a vertical line that only touches the graph once, then it's a function. It says if any vertical line exists. So if I move just a little bit to the left, I could draw a different vertical line that touches the graph more than once. So this one is not a function, so it fails. So not a function. So if we now go back to the one on the left, no matter where I were to draw a vertical line, every vertical line that's possible, if I kept drawing them no matter what, it would never touch the picture of that graph more than once. So this one passes, and it is a function. Similarly, for our last one, once again, no matter where I draw a vertical line, it would touch the graph only once. So that is also a function. So just be a little bit careful with that definition, because it says if there exists any vertical line that touches it more than once, it's not a function. All right, so the vertical line test has a cousin called the horizontal line test. And the horizontal line test is used to determine if a function is one-to-one. So, similar to the vertical line test, if there exists any horizontal line that intersects a graph more than once, then the graph for the function is not one-to-one. And you're probably saying, well, we haven't defined one-to-one yet, and I agree, so let's define what it means to be one-to-one. So a function is one-to-one if when f of x equals f of y, then x equals to y. So that's our official definition of one-to-one, and it's not very clear, and I realize that. So let's talk about what it says and interpret it. So a one-to-one function says that if we have two outputs that are the same, so if the output f of x is the same as the output f of y, what's our conclusion? The x and y were actually the same number. So what this is really telling us is that all outputs are unique. So going back to the example we started with in functions, remember, domain was our class and our range was grade. Our function would be one-to-one if once some student had a grade, no other student could get it. So that would mean in the class there could be exactly one A, there could be exactly one B, there could be exactly one C, exactly one D, and exactly one F. So when a function is one-to-one, it means that all of the outputs are not unique or the outputs can't repeat. So that's different than being the definition of a function. Functions say we can repeat the same output as long as it comes from different inputs. This, a one-to-one function, says that is no longer allowed, that all of the outputs have to be unique. All right, so then the horizontal line test gives us a graphical way to test if a function is one-to-one. So example 6 says, determine if f of x is 1 to 1 and f is equal to x to the 6th minus 2x cubed plus 1. So our strategy is we grab our graphing device and we draw a nice picture. So let's go to y equals, clear out anything that we have in there, and let's go with x to the 6th minus 2x cubed plus 1, and let's graph. So we get a picture that looks like this when we graph it. So if I were to draw a horizontal line, I would get 2 intersection points. So this fails the horizontal line test. So f of x is not 1 to 1. So, all right, so let's go ahead and resolve this. So we grab our graphing device, put it in, so we end up with x to the 5th minus 2x cubed, oh, missing a minus sign, plus 5x. So I draw a picture, and I get a graph that looks something like this. So it appears that no matter where I draw a horizontal line, it would ever only intersect the graph once, so this passes the horizontal line test. So then f of x is 1 to 1.